Okay, everyone. Uh, let's first start with the interesting part, your coursework project. Time flies. It's week 4 and time to start working on your project. The project I have defined for you is the design of active suspension system for the automotive industries. But the concept that you will learn from this project is applicable to many applications. If you are biomedical engineer or you are aerospace engineer, the concept is the same. For example, the suspension system can be used for the aerospace engineers as design of the landing gear of the airplanes, or for the biomedical students can be used as a suspension of the moving robots or moving medical robot system. The concept is the same, but to be specific here, I defined for your project in order to design a control system for the suspension system. I gave you a brief introduction how suspension system works, but what you need to do, you need to design the suspension system control based on this 2 degree of freedom spring mass damper system. As you see, we can model the suspension system, doesn't matter, it's the aeroplane suspension system or is the automotive suspension system or is the robot suspension system. We usually model the body of chassis as a sprung mass, or we consider a quarter of the vehicle in order to design a suspension system, active suspension system. So sprung mass MS shows the chassis mass. We model the tire with another mass, unsprung mass. The suspension can be modeled by 2 linear spring and damper, and tire as well can be modeled by a spring, linear spring. What we want to do, we want to design a proper control force U in order to improve the performance of this 2 degree of freedom system. The input to the system or disturbance to the system is the road profile, ZR. So you need to define or design a project such that for 3 types of the inputs, a step input, bump input, and 1 random input, to achieve this control specification. At least 30% of the maximum reduction of maximum overshoot, ZST, for the bump and step input, at least 40% reduction of settling time of ZST, 0 steady state error for ZST for both bump and step inputs. You need to improve the performance of the system by 30% reduction of root mean square of signal ZST, and at least 30% reduction of maximum amplification in time domain. To do that, you need to follow this step. First of all, as we discussed, yes? How can I do that? Is it from here?
Metal string. I can't see. Metal string.
There, on the right. On the right.
Oh, okay. There?
Yeah, thanks.
Good. So, to start this project, you need to start, and not need, you have to start the project by tonight.
Huh?
Okay?
By tonight.
From tonight, if you want to finish it by week 11. Okay. To be honest, don't leave it by at the end of the project. You need to start it today. Because, to be honest, I'm following your performance on Saturday, and I was totally surprised. More than 50% of the students haven't signed in Saturday. I think the last time was 2 or 3 weeks ago. Okay? And I posted several videos on YouTube and on Saturday, both of them. And just 10 or 15% of the students have watched these videos. So it looks that you need more motivation. So at the first I wasn't supposed to give you this project, but I thought that it's better to give you more motivation to be involved in the control system design. To do that, you need to first derive the equation of motion of the system. We talked in the first lecture about the equation of motion. As you know, I'm sure all of you know, the first step in control system design is deriving a proper model of the system. To derive the proper model of the system, you need equations of the motion of the system. What was the equation of motion? Or what is the equation of motion? Equations of motion are the set of differential equations that represent the dynamic performance or dynamic behavior of the system. Okay? You need to build up the equations of motion. It's very simple because you learned from the second year module how to obtain the equation of motion for the simple system. From your dynamic module as well, you know how to derive the equation of motions or build up the equation of motions. From year 3 dynamic module, Patrick is lecturing, for sure you know how to derive the equation of motion for the 2 degree of freedom system. In the next step, you need to write the equation of motions of the both uncontrolled and controlled system. Uncontrolled means open loop system, controlled means closed loop system. In state space format, you can do it right now. It's going to be, I will lecture the concept of the state space domain maybe 3 or 4 weeks later. But you can skip this step at the moment and work on the third part. You need to derive transfer function Zs over Zr because all specifications are defined based on the Zs. So output of our system is the vehicle body displacement and the input is road disturbances. So you need to derive the, this transfer function. Again, you know how to do that. To know or to have idea about the nature of the dynamics of the system, you need to define or find out what's the location of the poles and zeros of the system based on the transfer function of Zs over Zr. Next step, you need to plot the time response of the uncontrolled system subject to the given disturbances, the 3 disturbances in the project. For this one, you need to use MATLAB. Okay? You need to plot.
Just for the plotting.
For the plot and analyzing the control system. From this week, we will have, just a moment. From this week, we will have our tutorial in the lab. So you can work with MATLAB. I will post some other videos to give you information how to work with MATLAB and how plot and how analyze the system in MATLAB. If you want, you can watch. If you don't want, you can do by yourself. Yes?
So it's wait about 4 weeks before we do the uncontrolled and controlled system.
No. Okay, wait. It's going to be 4 weeks, maybe 3 weeks later, but wait. Then you need to analyze the system response in frequency domain by plotting the both plot of the system, again using MATLAB. Then you need to design a PID control. Next week, I will teach you how to design a PID control, or you can use the pole location controller. It's up to you which controller you want. You can use the design a pole location, or you can use the design a PID controller. PID controller, you know how to design, but more details will be given next week. For the pole location, again, when I teach the state space, next step will be designing of the control system based on the pole location approach or methodology. Next step, you need to compare the frequency and time response of both control and uncontrolled system. And at the last step, you need to justify how your control system works. You need to show how you have achieved those specifications have been defined in this project. Interesting? Yeah. I know, I totally understand your feeling. But you have no choice.
So you said just on the MATLAB.
Yeah.
How much of this is to know?
You need to know the basic of the MATLAB. whatever you need, I will post videos or you can ask me in the
We
first.
haven't done this course.
I know. But the objective of this course is, one of these objectives is to know how to work with MATLAB. Okay? Any questions? Yes?
So can we do point 5 onwards for week 8 or whatever?
It is all up to you. I need your report by the week 11.
So, but
What
are
is that you
gonna
want to do?
go
You
through-
can do it by yourself.
Are you going to go through the, what's it called, the uncontrolled control systems in about week 8?
As I said, it's up to you, whatever. But the best thing is that start with working with uncontrolled system or like uncontrolled system. When you're confident about the performance and dynamics of the system, then you start working on the control system.
Right. So we can do the uncontrolled system now.
Yeah. Equation portion is for uncontrolled.
Yeah.
Okay? Driving the master functions and the original part is for the uncontrolled system. Most of the part is for the uncontrolled system. Yeah.
How would we model the random disturbances?
I gave you. If you look at the
equation,
no. If you look at the random inputs, I define the random inputs here.
I don't really understand how I would apply this.
Random input for this project is a combination of 3 or 4 sinusoid inputs. That's it. Okay? Okay, guys. Any other question? Look, guys. I received some feedback from your students. Some of them found the videos I posted on Saturday useful. I think the rest didn't watch. So, but one comment I can give you on this module: don't pile up everything at the end of the module. You don't have enough time to study. Control is somehow different from the other modules. I know. When I was a student, I did the same thing. I did the same thing. But if you leave everything for the end of the module, it's not going to work for this module. Okay? You need to study. So if everything is all right to everyone, let's start another interesting lecture.
How many marks per question?
Pardon?
How many marks?
15% of your final. 15, 1 5.
How many marks per question?
Pardon?
How many marks per question?
It is out of 100, but I will scale down to 50% of your final module. Okay? And one more thing, your project is individual project, but feel free to do by yourself, as a group. But at the end, I need a report from each of you. You have 2 options. You can submit your report online through Saturday, or you can give me a hard copy of your report. I don't expect any of the reports be the same, because this is the design project, and my expectation is that everybody has own justification for the construction. Okay? But I don't mind if you prefer to work together as a group or work individually. It's totally up to you. Okay, guys. One more thing I need to recommend to you. I record the lectures I give you every session and post on Saturday. Maybe most of you are not aware of that because you haven't found it in science. But again, the objective of recording these videos or the lectures is to help you to refresh your memory after the class. If you leave it again, look, it is important to attend in the class. I don't want if you come or you don't. What is important for me, to learn the control. If you think that you will learn from the videos from home and you don't need to attend, it's up to you. But from my objective, my aim is that you come to class. I'm sure you will get 20 or 30% of what I teach you here in the class. But the rest can be learn from the videos. If you come to class, maybe you don't get which part is not understandable to you, or maybe you get that the whole lecture is not understandable. But it doesn't matter. When you go home and watch again the video, it will help you to digest the concept much more easily if compared to if you don't come to the lecture. But as I said, it's up to you. My objective is that you learn control system. I wish all of you get A+ in the final exam. I do my best from my side, but the rest is up to you. So, let's start. Last week, we talked about the effects of the zeros and additional poles on the response of the standard second order system. We discussed how the dynamic response of a second order system will change if we have additional zeros or additional poles on the transfer function. We also talked about the stability of the system using the root criterion. Now we know how to check the stability of a complicated system by the Routh-Horvitz or Routh criterion. This week I will start a new concept. To be honest, till last week I was just reviewing what you learned from the second year module. Something new, but 80% of what I talked and discussed was about reviewing of the year 2 control. From now on is most new concept. In new chapter of this lecture, I will talk about this module. I will talk about the basic equations of the control system, mostly feedback control system. I will also talk about the control of steady-state error system type of the system. And at the end, I will talk about the control design using the PID technique. I know most of you know how to design the PID control, proportional integral derivative control, but in this module, I will give you more in-depth information or details to how to design the PID control system. Okay, so for the feedback system, we know, all of us know that the feedback system have some advantages. As a major goal or objective of the control system, control design, we can say that we can use the control design as a tool to keep the error small. What's the error? In dynamic system, any type of dynamic system, we have one output and we have one desired input. The aim is that because using the nature of the system is not possible to get always the best response from the system. So we need to have somehow modify the structure of the system to get the best or desired response. So we give the desired response to the system. For example, let's say we ask the system to have such a response. So how we can check we got the desired response? We have the output, compare it to the input, make an error. If an error is 0, it means that the output is exactly the same as input. Correct? If we have huge error, the difference between output and input, it means that the system doesn't work properly. So the objective of the control system or feedback control system is that to make that error close to 0. Okay? I'm looking for a more visual example. Let me see if in terms of the human body, if you're hot, for example, your body gives you some feedback. Okay? I'm hot. What do you need to do? You need to change your clothes. Okay? It's kind of a feedback control system. Your body says that I want to feeling some 25 Celsius temperature. What your skin gives you feedback is not 25, it's higher than 25. So you change your clothes, and when you reach to the 25, your brain says that, okay, that's fine. So what's your controller is your brain. What is your sensor is your skin. Okay? And what's the control action? Changing your clothes. So it's such the control system. The most sophisticated control system in the whole world is the human body. What kind of sensor do you have? Skin.
Feelings in
You have eyes, you have skin, you have ears, you have nose. So they are different kind of sensors. What's the processor of this control system? Is your brain. Okay? What's your action? Whatever you can do by your muscles. In fact, the actuators are muscles of your body. Okay. Now we know what we want to do. In this module, as I discussed in the first session, we will work on linear time invariant transfer functions. We have many methodologies to work or deal with the nonlinear complicated time invariant system. But if you know these basic control systems, which is the case for the 80% of the applications, then you can work on the more complicated systems. To be honest, the engineer designed the different application 100 years ago using this concept. And now still they are working using the same control system. I think the PID, I'm not sure, but the PID designed around 150 years ago. So it's not new. And still 90% of the industry using the PID controller. Okay? So if you learn PID, it's good, you will have a, or if you know the basic I'm giving you in this lecture, you will have a strong fundamental to know the control system. If you are interested, next step you can choose your individual project or MH project for the advanced control system or for advanced applications. So again, as we discussed in the first session, the first step of the control system design is to drive the equation of motion or to have a proper model of the system which we want to control. If this system, this model is given, the model can be given by the set of equation of motions, differential equation, or by a transfer function. If we have this information, then we need to define the proper specification for our control systems. As we discussed again last week, the most important and not negotiable specification is stability. The system should be stable first, then we can reach the other specification. If the system, if your control system is somehow that make the system unstable, is out of question. Your mark is 0. Okay? But if you're sure about the stability of the system, then we can talk about the other specifications. What type of the specification we have? The permissible steady state error in the presence of a constant or bias disturbance signal. We design a control system. We have a model. Model is a mathematics. And it is a linear model, which is different from, which is very simplified case of actual model. But we need to make sure our system, the controller we have designed, can work in different situations if we have different type of the disturbances in the system. I will talk about these topics more, but just to give you an idea. The other one is that the permissible steady error while tracking a polynomial reference signal. What type of, if you remember from the first session, what type of the control system do we have? How we can classify our control systems? One way of classification is open loop or closed loop system. Another one was regulator control system, trajectory tracking control systems, servo-mechanical control systems, different type of the control system. If you look at the lecture notes, you will see what type do we have. Another one is that the sensitivity of the system transfer function to changing in model parameters. What does it mean? We design a control system for a new product. Everything is perfect. We have the exact model. The model is very well matched with actual system, but after a while, the system will aging and the parameter will change. For example, you design a controller for the ABS controller, active anti-braking system controller, based on the properties of the tire. But the tire is new, and the properties that you have is for the new tire. Where after 1 or 2 years, the tire will get old and it will lose some properties. So as a very simple case, a stiffness of the tire will change. Does the system work still with that change of the parameter, or for how percentage of the variation of the parameter the system still will work properly? Okay, this is the topics that you need to make sure about it when you design a control system. And again, you need to check about the transient error of the system, subject to the step input or other type of the standard systems. As we discussed in the second lecture, second session, we have two types of the responses. One is the transient response, one is the steady state response in time domain. Okay? We need to make sure that the system works properly in both parts of the time domain response. Transient response and steady state response. So this is the topics that I will talk about it in this session, next session, and most probably third session for this chapter. Okay, so let's start again. What's the advantages of, and summary of what I have talked about so far? What's the advantage of the feedback control system? As a brief, reduce. Okay, reduce the steady state error. Correct?
Account for disturbances.
Pardon?
Account for disturbances.
Exactly. It makes the system robust against disturbances. What else?
More stable.
Stabilize the system on a stable system. Exactly. So far 3. Makes the system robust against disturbances, reduce the steady state error of the system, and stabilize an unstable system. What else? We have one more.
Reduce the sensitivity.
Pardon?
Reduce the sensitivity of the transfer function.
Sensitivity of the transfer function, exactly. Who was talking? Exactly. Good. Happy to see that. Okay, so feedback can reduce the steady error in response to the disturbances. You knew that. You knew from the module year 2 control system. But mathematically, how is it possible? I will let you know in this session, hopefully, if I have time. Feedback can reduce the steady state error in tracking a reference. Feedback can reduce the sensitivity of a transfer function to parameter changes. These two are subject to the disturbance, relates to the steady state error. The third one, the sensitivity or robustness of the system. And the fourth one, feedback can stabilize an unstable system. I hope you didn't look at your lecture notes and answer this. My assumption is that you didn't. Let me be positive. Okay, what are the disadvantages? What's the most important part of any mechanical or engineering design? No, more general.
Component.
Complexity.
Complexity can be one, but in terms of industrial point of view.
Cost.
Cost, exactly. You need to reduce the cost of your design. But if you want to design a feedback control system, you need to have some sensors to measure the feedback, measure the response of the system. Usually, the sensors are not cheap. The range of the cost change from £10 to almost £100,000. Depends what type of the sensors you are looking for. So if you want to design a control system, for sure you will increase the cost of the design or the cost of the manufacturing. Because you need to add or integrate at least one sensor. At least one sensor. I know BMW from one of my friends working in BMW state 4 or 5 years ago. BMW uses in fourth generation BMW Series 4, I think, 250 sensors to control the whole behavior of the system, dynamic of the system. 250 sensors. But for the simple control system, you need at least have one sensor to measure the output of the system, okay, which adds some additional cost. And again, if you use the if you use the sensor usually, because they are very sensitive devices, add some noises to the dynamic of the system, which add complexity to the performance of the system. But we have many ways to deal with such issues, the noise issues. I will talk about the noise as well in this part of the lecture. Again, complexity. The design of the feedback control system is more complicated than design of the open loop control systems. So when you design a control system, you need to be aware of these disadvantages. Okay. So to start, in this lecture and in this session and next session, I will talk about the basic equations of control system. For the open loop system, we have such a transfer function. We have input shaping, which is transfer function is HR. Controller, which is transfer function is DOL. OL stands for the open loop. And plant G. What's the plant G? Plant diff transfer function G is the application or the system we would like to control. Or we want to control it such that gives us a desired performance. Okay? Controller is what you will need to design. What's the input shaping? Any idea? If my output is displacement of a spring mass damper, what's the dimension of the displacement? Usually meter. Okay? If I have such output, what can be my input to the system or reference input?
Force.
Force?
Newtons.
Pardon?
Force in newtons.
Force in Newton? Any idea? Your reference input and your output have the same dimension. You are comparing them. For example, your dynamic system gives you displacement. You have a desired displacement, correct? As a reference. You say that I want to have this displacement response, for example. But the actual is something different. We want to control the design a controller such that the output of my dynamic system is close, at least close to the exactly the same or close to reference signal. Correct? But the point is that the input to controller is usually voltage. We have the electrical system. We need a device to convert our reference input to voltage. This can be done by a input shaping. So input shaping convert the dimension of the input to voltage. It's a mechatronic system. We have the mechanical, most probably our plant is mechanical system. Controller is the electrical system. What kind of electrical system? Is the computational system, which calculates the voltage. Okay, if I want to define, I assume I have a disturbance to my plant. I'm thinking of give you some examples, practical examples of a disturbance. Anybody can give me any example of the disturbance? What does it mean, disturbance? Disturbance is the unwanted signal to the system, okay, which can damage the performance of my control system response. For example, I'm talking, somebody saying noise to me. So it's kind of a disturbance, correct? So disturbance is something that affects the actual performance of your system. Can be anything. And is always to the plant. If I say consider the disturbance as the input to the plant, the output will be in this form. Why? What's the summation for? How can I get to this? How can I calculate my open loop output? Tell me, in this case, how many inputs do I have? 2 inputs. What are they? What? HR is a device. Device can't be input. R and W. Reference input and disturbance input. And I made a strong assumption. My system is linear. What concept is applicable to this linear system? Superposition. Correct? If I use the superposition, what does the superposition says? The output of the response, the output of the system is the summation response of each input. So, for simplicity, to calculate the overall output of the system, first I assume, based on the superposition, I ignore W, and I would just consider the reference input. The transfer function between Y and R is what? All transfer functions are in series. So will be multiplication of this transfer function. Will be HR multiplied to DOL multiplied to G. So transfer function from Y to R is HR HDG, which means Y, the output is HDG multiplied to R. So this is the response subject to the reference input. But I have another input. Again, based on the superposition, I ignore this input and I just consider the output subject to the disturbance input. What's the block diagram in the feed-forward path of this input-output? Is just G. So the Y subject to the input will be GW. So the overall response of the system is the response subject, the summation of these two responses. This one is the response subject to reference input, and this one is the response subject to disturbance input. And the total response is summation of these two responses. Correct? Any question? You're too close to the screen, aren't you? To make you sleeping. Okay, anyway. Any question? So, assumption is clear to everybody. Go to next step. But again, as I said, the most important objective in the control system is to make the error zero. What's the error? Is the difference from the output and the reference input. If I define the error as difference from the reference input and the actual output of the system, the reference is R, but the actual response is here, given here. So if I subtract the output and if I substitute this response to this relation, I will get this difference, which if I do some calculation, the response will be 1 minus TOL R minus GW. TOL is the transfer function from the Y to R, which is HDG. in this module, we mostly work on this variable, error. We want to control the error. For the open loop system, the transfer function from the output to two disturbance to two inputs will be based on this relation. But as I said, because of the advantage of the closed loop system, we would like to work on the closed loop system. What's the transfer function, or how we can calculate the error of the closed loop system? For the feedback control system, which figure given below, but you don't see any figure so far, we want to see how we can calculate the error. Again, look, what we want to control is the plant. With transfer function G. To control the plant, we need to have some information about the output of the system. So we need to take feedback. This is why, and why is the output of the system? The response, we would like to have a desirable shape or response. To measure that, we need a sensor. So sensor takes feedback from the output of the system. By the output of the sensor is just a response. We need to justify the response. We need to see is okay or not. We need to compare it with something. We need to compare it with reference signal. So we have the desirable response or reference signal goes to the input shaping converted to voltage. The output of the sensor is voltage as well. So we compare the output or the actual response of the system with the reference input to build up the error of the system. Okay? Plus, minus gives you error. The error goes to the controller, and we adjust the error, and based on the error of the system, the controller generates a proper control action in order to adjust the behavior of the plant. Usually between the controller and plant, we have actuator. Because the output of the actuator is output of the controller is voltage. But what we want to give the plant is usually mechanical thing, force, rotation, something like that. So we need to have actuator between controller to plant, from the actuator to plant, to transfer the control action. But in this module, I ignored the actuator. We have two other input signals as well. One disturbance to plant, and another one is sensor noises. So for the proper control design, we need to consider these two additional input signals. Any question? Okay. So, yes?
So in a real application, what would the plant be? In a real application, what would the plant?
Plant, we have many things. One plant can be this room. We want to control the temperature of the room. Okay? One can be automotive. We want to control the performance of the motor. For example, if you go to the IC road with a high speed, which is the case for most of you as a teenager or young people, and me as well. If you want to go to the IC road, the system is unstable. We want to stabilize it. What ABS do, or traction control do. Or if you want to send a missile to a space, you need to control the direction. So for example, if you want to control a missile, you, by the sensor, measure the angle of the missile, and the controller tries to keep it straight to Mars, or to Moon, or whatever. Okay? So, I think we don't have time to go further. Let's keep it as it is. But please read your lecture notes, watch the videos, talk to my office, do your tutorials, and I posted some videos solving some problems from the years to module. Do it by yourself.
Starting the course with me.
Just a moment, please.